Hello, I am Ahmad, and in this video we are going to talk about elastic and plastic section modulus, and we calculate the plastic and elastic bending moment for a section which is made by elastoplastic material. Let's assume that we have a cross section which is not rigid and is made of a elastic, perfectly plastic material, and it's going to be under a load sigma and epsilon, and the graph shows that the material which is going to be used is elastic, perfectly plastic material. First of all, we need to derive to the calculation of stress in a cross section when it is in elastic phase. If we have a cross section or a tiny element of this cross section, which is under a positive bending moment, it starts to bend due to bending moment. So in this calculation, we assume that the beam or the element follows the Euler-Bernoulli hypothesis. It means that the length of the element h is quite long compared to its dimension, especially its depth. So if the depth is also significant in terms of the length, then the Euler-Bernoulli hypothesis is not valid. The difference is that if we have a very deep beam compared to its length, then the shear also would affect, and that beam is not Bernoulli or Euler-Bernoulli beam. It is called Timoshenko beam, and then the deformation and the equations would be completely different. But we are talking about a beam which is a one-dimension element as a member, and it's long enough. Usually L divided by the depth should be greater than 15, 20, that this hypothesis is valid. So in this case, there is another video number 1 in this playlist that you can watch, and it's about how to derive to the deformation at each elevation of the beam from the neutral axis. So we continue from there, and if you're interested, you can have a look on that video as well. If this is our element, which is bent now, and if we assume that this is the neutral axis, and we are interested in a line which is with the distance of y from the neutral axis. In the other video, we calculated that delta differential of deformation at the height of y is minus kappa y dx. So S train is deformation divided by original length. So if you are talking about a very small part of the element, the length before deformation is dx, and the deformation after applying the bending moment is d delta y. So it will be d delta divided by dx, so it will be minus kappa y. This is the strain at each level from the neutral axis. Now, if we sketch the element, it doesn't matter what shape we are talking about. and if this is the neutral axis, and we assume that we are talking about a tiny ribbon in this elevation, which is with the distance of y, and the area is dA. So the force in this level will be divided by the area, and we have sigma at the elevation of y. So now if we want to calculate the bending moment of this ribbon by respect of the neutral axis, we need to calculate the force and then multiply the force by the distance to the center or to the neutral axis, which is y here. So differential of moment will be differential of force times y. And differential of force will be sigma times dA. Sigma is a constant value at the elevation of y, and then dA is the differential of area, so stress times area will be the force. As a result, dm will be sigma at the elevation of y times y times dA. So this is the equation, no doubt. Now, if we come back to the former video 005 about the introduction to plastic bending moment capacity, we remember that sigma can be written as E epsilon if we are in the elastic phase. So if we are talking about elastic, then we can use sigma equals to E epsilon. If we are not in the elastic phase, then this equation is not valid. If you remember in the other video, we had rod B, C, and D, and before B, C, and D became plastic, we used the elastic equation for calculation of deformation of the rod or for the stress. So here also we can use sigma equals to E epsilon if we are in the elastic phase. It means that none of the fibers inside the cross section would be in their plastic phase. So differential of moment will be E times epsilon at the elevation of y dA. By recalling equation I and substituting instead of epsilon y, then differential of moment will be E times minus kappa y times y dA. And finally, we can write down that this is minus E kappa y square dA. So this is for a tiny ribbon of the element. If we want to have the total moment that is applied to this cross section, then we need to make the integration for the entire section. So moment will be integration of minus E kappa y square dA. In a section that we are at a certain point of the beam, kappa is constant. It's the curvature. E is the material property, which is constant. So we can take these two off from the integration. Summation of y squared dA is called moment of inertia. It's a cross-section property. As a result, moment will be written as, if we go with positive value just to have the number, so it will be E kappa I. And also kappa is 1 divided by the radius of curvature. So M will be EI divided by rho, or famous equation, 1 divided by rho will be m divided by ei. So this equation is only valid if we are in the elastic phase. Now again, by recalling sigma equals E epsilon, let's name this equation as equation 2. Sigma is E times epsilon. And epsilon, by using equation 1, can be written as minus kappa y. So it will be minus kappa times E times y. And kappa is 1 over rho, so it will be 1 over rho E times y. And now we can use m divided by ei instead of 1 over rho, so it will be minus m over ei times E times y. We can cross E, and then sigma in each elevation can be written as minus m times y divided by I. So this equation is valid only if the section is in elastic phase. Now if we look at our cross section, with its neutral axis, and if it is under positive bending moment, the upper part of the cross section will be under compression, and the bottom part will be under tension. So sigma will be maximum if y is maximum, because as we noticed, sigma is calculated according to m times y divided by I. I is the property of the cross section, which is second moment of inertia, and moment in a certain point is constant. As a result, sigma is maximum when y is maximum. So here, sigma max can be written as m times y max divided by I. So if we assume that the maximum distance from the furthest point of the cross section to the neutral axis is called c, then we can say that sigma max is mc over I. The negative signs shows that if the value is negative, then it is in compression. If it's positive, then it is in tension. So if we ignore that to have the value, then sigma max will be mc divided by I. C can be for the compression side or for the tension side, and it can be different if the cross section is asymmetric. But if it is symmetric, at least about one axis, then we have C max as a constant value in both sides. Now if I write it down by m divided by I over C, then we have this I over C for a section which is called section modulus. And it is written by either W or S, W in European countries, S by American countries, so it doesn't matter, section modulus or W, both are the same, I divided by C. And this is elastic section modulus. Why it is elastic section modulus? Because in our calculation, we assume that we are in the elastic phase. So this is W elastic is I divided by C. Now, if we look at the cross section, how the stress look like? Assume that this is our cross section, which is under a certain value of bending moment. So we can see that the furthest point of the cross section from neutral axis is always under maximum normal stress due to bending. So here, and as far as the equation is my divided by I, m and I are constant, so sigma is in a linear relation with y. So it's a linear distribution of the stress. Compression, 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 and then tension, 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 and tension. In the video number 5, we solved also the value of P that the first element becomes plastic. So if you remember, the value of P was 191. It meant that before 191, all the rods are in the elastic phase. Here also, if the bending moment is less than a certain value, then the whole section is in elastic phase. So in the Euler-Bernoulli hypothesis for the beams, we know that the plane will remain plane. It means that after deformation about its neutral axis, the section will remain plane. Like in the other example that we assume that the element is completely rigid. We can assume that the section is completely rigid and it is bent, but it still keeps its form, which is a plane. Now, by increasing the moment m, we can easily see that the first fiber of the cross section that would yield is the furthest fiber. So it means that if we want to calculate the minimum value of moment that at least one of the fibers in the cross section become yield, we need to calculate for the maximum stress. So as far as we know, sigma max is m divided by w. I write w elastic because we are in elastic phase. So if this value equals to sigma y, then we can say that we found the yielding bending moment. So sigma y is my divided by w elastic. So my is sigma y times w elastic. This is like how we determined py for the other example. So we calculate elastic section modulus, multiply it by sigma y of the material, and then we have the yielding bending moment. So now after this, if we start to increase the bending moment by referring again to the other example that we had, we expect that sigma in the furthest fiber, which now is sigma y, remains constant and it cannot go further than that. So then the next fiber starts to become plastic. Then we increase the load for the bending moment again and again, the same in the other side, until the entire cross section becomes plastic. Now this moment is m plastic. What is the difference between this and elastic is that now the stress in the entire cross section is sigma y. So for the calculation of m plastic, now we can say if we have this cross section and we are looking at one tiny element, which is dA, and here this is the neutral axis. with the distance of y. Now we expect that the stress in this level is sigma y. As a result, differential of force in that elevation, let's write it down as y, will be sigma y times dA. And then the differential of moment is now dF at elevation y times y. If we substitute dF in the latter equation, dm will be sigma y times dA. Now for having the entire moment, we need to take the integration. Sigma y is a constant value, integration of y dA. So if we compare this equation for plastic moment with the equation for yield moment, we can see that here this is sigma y, which is the same as sigma y in my. And the difference is that W elastic is calculated according to division of or fraction of moment of inertia divided by the furthest distance from the neutral axis. But here we have the first moment of inertia summation in the positive and negative direction or side of the cross section. This summation of y dA is called W plastic. So the difference is that in elastic calculation, we need to calculate the moment of inertia and divide it by the furthest distance to the neutral axis. And in the plastic section modulus, we need to calculate the summation of distance times area of each fiber. So as a summary, M elastic is sigma y times W elastic, and M plastic is sigma y times W plastic. W elastic is always moment of inertia divided by C, and W plastic is integration of y dA. And if you have a certain cross section, you can write it down sigma y times A. YI. To have a better understanding, we go through the calculation of these two for one section, which is rectangle, and then we go through the other example. If we have a rectangle cross section with the width of B and height of H, so we know that the neutral axis is in the center. Moment of inertia is BH3 divided by 12, and the furthest distance from the neutral axis in both sides is H divided by 2. So W elastic is I divided by C, so it will be BH square divided by 6. For W plastic, we don't need to calculate moment of inertia. Instead, we need to calculate the summation of Y times A. So W plastic is the area, which is B times H divided by 2 times the centroid of this section to the neutral axis. So this is H divided by 4. H divided by 4. So this is for the upper part of the cross section. For the lower part, we have the same value. So it will be plus B H divided by 2, H divided by 4. So it will be BH square divided by 4. We can see that always W plastic is greater than W elastic. And then we can calculate what is the maximum elastic moment or maximum plastic moment. Now let's have another example for one eye section. Let's say 200 millimeter with the thickness of 12 millimeter. And the height is 280 and the thickness of the web is 6 millimeter. Now, for W elastic, we need to calculate moment of inertia. And as far as the cross section is symmetric, we can say that the neutral axis is in the center. And here is 140 millimeter. So moment of inertia will be, there are plenty of ways to calculate. I calculate by the assumption of this rectangle, which is 200 times 280 cubic divided by 12. Then I will deduct these two rectangles. As far as they are in the center, so I don't need to use AD square. So minus the width of this will be 200 minus 6 divided by 2. So 97. So 2 times 97 times, and the height will be 280 minus 2 times 12. 256 millimeter. 9.5 10 power by 7 millimeter power by 4. And C is the furthest distance to the neutral axis. As a result, W elastic will be I divided by C, 9.5, and power by 7 divided by 140 millimeter. 6.76 and power by 5 millimeter power by 3. For calculation of W plastic, we need to write down sigma AI times YI. I sketched the cross section one more time that it is easier to go with a fresh sketch. So this is the neutral axis, and here we can go through the flange. The area is 200 times 12, and the distance is 140 minus 6, 134 millimeter. And as far as I have two sides, the same flange, plus then we have web, which the height is half of 256. And the thickness is 6 millimeter. 128 times 6 is the area times half of 128, the distance, and then we have two sides, the same elements, so it will be multiplied by 2. So it will be 7.41 10 power by 5 millimeter power by 3. But what about between? So we can calculate W elastic, we can calculate W plastic, and then we can calculate elastic moment and plastic moment. What would happen if the moment is something between? Before that, let's have a simple calculation for one rectangle cross section to see how to calculate it. Let's say we have a cross section with B equals to 120 millimeter and height of 200 millimeter. W elastic is BH squared divided by 6. So 120, 200 squared divided by 6, it will be 800,000 millimeter power by 3, and W plastic is BH squared divided by 4, and it's 1200,000. Let's assume that we have a material which sigma y is 250 megapascal. Then M elastic for this cross section will be sigma y times W elastic. So it will be 250 megapascal times 800,000. So it will be 200 kilonewton meter. For plastic moment, sigma y times W plastic. 250 megapascal times 1200,000. So it will be 300 kilonewton meter. And it is better if we sketch these two results to see what would happen in the cross section. For the first one, the height is 200 millimeter. It means that if we apply moment elastic, which is 200 kilonewton meter, then the furthest fiber of the section will approach the yield limit, which is 250 megapascal. And other fibers are with the lower value of sigma y, as we can see here, and it's linear. And if we apply the bending moment in the plastic phase, or the plastic bending moment, which is 300 kilonewton meter. Now all fibers are in their yield limit. The elastic moment is like in the other example, force is at the level of 191 kilonewton, and in the other one is when the load in the other example was 245.5 kilonewton, something like that. So we might be interested in something between. For example, partially the cross section is now plastic and partially elastic. There are many more resources and also some equations how to deal with that. The easiest way might be just to sketch the stress distribution or following the equation that is given for rectangular cross section. I personally prefer to sketch by the stress distribution, as it is regardless of the cross section and you don't need any equation in your mind. So now our question is, if the moment is 250 kilonewton meter, what is the plastic depth of the cross section? Or you can say, what is the moment that 1/4 of the cross section is plastic? So this is a little bit challenging compared to the other case. So now we know that as far as 250 is greater than 200, we know that it is not fully elastic. And as far as it is less than 300, So it is also not fully plastic. So it will be something between. You can easily sketch the cross section, and we don't know what is the height of plastic behavior. You can assume something like y, and also in the other direction the same, and the rest is elastic. And we are looking for this y height. What do we have? We know that the bending moment is now 250 kilonewton meter. The only thing is to sketch the cross section. So after a while you might not need this anymore, because you know how to calculate it without the 3D sketch. But for now it is worthy if we sketch it. So here we can assume that this is the plastic side, and then the rest is elastic. So here we write it down as F1, F1, and the rest is elastic, this part. We can write it down F2, F2. And now if we look at this from side, again, coming back to the side view, F1 is working up to the height of y, and it's a constant on rectangular distribution. And then the rest is triangle. If the distance for the plastic side is y, the total depth of the cross section was 200 millimeter. So then the elastic side in the compression will be 100 minus y, and the same in the other side, 100 minus y, and this is y. As far as F1 is applied in the constant or rectangular stress distribution, it will be applied in the center of this. And then the distance to the center will be 100 minus y divided by 2. F2, on the other hand, is applied as far as the distribution is triangle. It is in the distance of 2/3 times 100 minus y. Now the only thing that we need to calculate is F1 and F2. So F1 is sigma times A1. So A1 here is y. The width of the cross section was 120 millimeters. So the area is 120 times y. And we know that sigma is now sigma y because it is now plastic. So this is also sigma y. F2 is not sigma times area because it is triangle. As a result, it will be the average value between the top and bottom. So the top, it is sigma y, and the bottom is 0. So it will be sigma divided by 2 times area of 2. So area of 2 is with the height of 100 minus y and with the width of 120. So it will be sigma y divided by 2 times 100 minus y times 120. Now, the only thing that we need to calculate is the moment which is coming from F1, F2, F2, F1. So the moment will be F1 times 100 minus y divided by 2 times 2 because we have in both sides, plus F2 times 2/3 of 100 minus y times 2 because it's also in 2 sides. Now we can substitute the values that we have. This is 250 and powered by 6 Newton millimeter. F1 is 250 megapascal times 120 times y. This is millimeter square times 100 minus y divided by 2 millimeter times 2. So Newton per square millimeter times millimeter square Newton times millimeter. Plus F2 250 divided by 2 megapascal times 100 minus y times 120 millimeter square times 2/3 of 100 minus y times 2. So the only unknown here is y. Simplify this. 250, 250, 250, and 29.3. So we can see that it would be reasonable. From here I can calculate F1, F2, and so forth. So here I think it should be F2. Not Fy. So the question was, what is the plastic depth? So the plastic depth is 2 times 29.3 millimeter, 58.6. You might see some equations in other sources that they offer the equation, but they are valid only, for example, a certain cross section. But this method is applied to any cross section, it doesn't matter. Let's go through one more example. For example, for a 1I section, the same cross section we used earlier for the section modulus calculation. 12 and 6 millimeter. And W plastic was 7.2 41 10 power by 5, and let's assume sigma y is also 250 megapascal as former example. Now elastic moment will be sigma y times W elastic, and it's 250 megapascal times 6.7610 power by 5. So it will be 169 kilonewton meter. And plastic moment will be sigma y times W plastic, which is 250 megapascal times 7.41 10 power by 5. So it's 185 kilonewton meter. It means that when the bending moment is less than 169 kilonewton meter, then the entire cross section will be in elastic phase. And if the moment is increased to 185, then the whole cross section will be plastic. Now, what is the bending moment? That the flange will be plastic. So it means that we are talking about the moment that is greater than 169, but it is not 185. So it's a partial plastic cross section. This is very straightforward calculation. You sketch the cross section. And we know that only the flange is plastic. This is another way of a sketch. So it's the concept is the same, but you can sketch it differently. Sigma y, sigma y, sigma y, sigma y. It is easier if we have the distances clearly from the side. So 12 millimeter, and it was 128 millimeter, total 140. So I would prefer to sketch the flange as a separate entity. Plus, ignore the flange and sketch the web. So here we know that the flange is completely plastic, and sigma y, I can write down this is F1. And here we have F2. Here also we have F1. And as far as its rectangle distribution, it will be in the center of the distribution. So it will be 128 plus 6, 134 millimeter. In the web, we have sigma y and its triangle distribution. as far as it is triangle distribution, then the force will be in the 1/3 of one side, 2/3 the other side. So it will be 128 divided by 3, which is 42.7 and 85.3. Now I can calculate F1 sigma y times area of the flange, because the entire flange is now plastic. So sigma y is 250 megapascal and area of the flange is 200 times 12 millimeter. 250, 212. So it is 600 kilonewton. F2, sigma y in one side, 0 in the other side. So it will be sigma y divided by 2 times the area of this web, which is 128 times 6. And I can write 250 megapascal. So it will be 125, 128, 6, 96 kilonewton. And the only thing is to calculate what is the moment here. So the moment is F1 times 134 millimeter times 2 plus F2 times 85.3 times 2. So by substituting these values, so it is 177.2 kilonewton meter. It should be between elastic moment and plastic moment. Let's check. So 169 is between 177 is between 169 and 185. The other question might be calculate the depth of plastic of this cross section if the moment is, let's say, 180. So if the value is greater than 177, then it means that flange is completely plastic and the partial distance of the web is also plastic. If it's between 177 and 169, then it means that a partial depth of the flange will be plastic. One would ask that if we do not have 177.2, then how we can know if the flange is plastic or not. If you do not have this 177.2 kilonewton meter as the moment that the entire flange will be plastic, then I would advise you can calculate first what is the moment that, for example, flange will be completely plastic. Then after that, you can decide with the given equation if your plastic depth is inside the flange or a partial part of the web is also plastic. So we can have one example and continue this example with the same example. Now, if M equals to 180, what is the plastic depth of the cross section? So here for the solution, we know that moment is now 180 kilonewton meter and it's greater than 177.2 kilonewton meter. As a result, partial part of the web is also plastic. Now we can sketch the entire system. So we know that some part of the web is also plastic, but we don't know what's the depth. And then it's elastic. F1, so we are familiar with that. We have that value, it is 600 kilonewton. And the Y1, we also have it. It was 134 millimeter. And then let's say this is Y. F2, the area is Y times 6 millimeter times sigma Y. And then Y bar 2 is, it was 128 millimeter. So it will be 128 minus half of Y. And here we have also F3. So F3 will be 128 minus Y times 6 millimeter times sigma Y divided by 2 because it's triangle. And Y bar 3 will be 2/3 of this height. Now we can write the equation for bending moment. Bending moment will be F1 times Y bar 1 times 2 plus, or we can just write 2 factor 2 because we have the same principle for all of these values. F1 times Y bar 1 plus F2 times Y bar 2 plus F3 times Y bar 3. So there is a very important, if you are using MATCAD, for example, then you don't need to be worried about it because everything is, if you use the units for the calculation. If not, you can, you need to notice that if you put, for example, F1 as 6 kilonewton and then use Y and 6 and sigma Y as 250 megapascal and millimeter, then the result will not be reliable. So how to solve it? M is 180 10 power by 6 Newton millimeter equals to 2 times F1 is 600. I go with 600,000 as Newton, that I don't need to be worried about the dimensions. And this is also millimeter. Plus F2 is now 250 megapascal times 6 times Y. This is now Newton times 128 minus Y divided by 2 and plus 250 divided by 2 times 6 times 128 minus Y times 2/3 of 128 minus Y. And then you can solve it. So 11.82 millimeter. So it means that the plastic depth in total will be 2 times 11.82 plus 12 millimeter. This is from the flange that we know it is already, and this is from the web. So 12 plus 11.82 times 2, it is 47.64 millimeter of the depth in total. Positive and negative side will be in plastic. And if you solve it in another way, let's say the given moment is 172, and then you assume that the flange is totally plastic, and you calculate according to this equation, then at the end y will be negative. But it is not the correct answer if you just say that, okay, so y is negative, then I can reduce the 12 millimeter from the flange from that negative value, and then it's the depth of the flange, which is plastic. No, you have to come back to the to get to the beginning and now assume that the flange partially is plastic, and write the equation again and solve it for the correct answer. That's the end of this video, and we went through the elastic section modulus, plastic section modulus, and how to calculate them for a symmetrical cross section. Later on, I will try to record another video regarding the asymmetric section, like a T section, how to calculate the neutral axes in elastic and plastic, because it might be different according to the cross section. And also in this example, we went through the elastic and plastic moment calculation, and also calculation of moment between these two limits, and also the plastic depth in each case. Thank you for watching. See you next time. Bye.